Yay!
Yay! Hey, what's up? This time, we're going to imagine the following situation. Suppose you're in a car, and there's something hanging from the rearview mirror, right? And then the car is going to accelerate like this way. So it's taken off from a stoplight. What happens to the thing that's hanging by the mirror? Well, it seems, from your point of view, maybe in the passenger seat, it seems to go backwards, right? And the car accelerates forwards. We're going to talk about that, what it looks like from an outside viewer and what it looks like from you in the passenger seat. Just for a moment, imagine you're looking at this thing from outside the car. So what you see is you see this thing as the car starts going forward, it makes an angle with respect to the vertical, and then it goes forward with the rest of the car, right? Okay, so let's talk about how to set this up. So here's the little hanging thing. Maybe it's on a string, so there's some tension going up to the right, and then it's weight mg, and then there's the angle theta, right? And so overall, there's going to be an acceleration towards the right. So let's see what the acceleration is for a given angle. The idea is that we can use this angle. If you measure this angle, you can use it as a sort of an accelerometer to figure out how fast the car is accelerating. Because the faster it accelerates, the more it accelerates, then the greater that angle is going to be. If it accelerates very gently, that's going to be almost totally vertical. Okay, so let's see how to set this up. This is a pretty simple free body diagram, so we're just going to do the usual thing in the x direction. What do I have in the x direction? It looks like, well, that's a vertical angle, right? And I want the x direction, I want the horizontal component of the tension, so it's opposite to the angle. And if it's opposite to the angle, that must mean it's sine. So t sine theta. And that's it, right? That's all that's happening in the x direction. So t sine theta is equal to m times how this thing is accelerating. And in the y direction, what do I have? Well, it must be the other one, t cosine theta, and then I got minus mg, because gravity's pulling down. It's not, let's suppose it's not doing anything in the y direction, so that's going to be 0. All right. So in that case, what I'm going to do is I'm not trying to find the tension right now anyway. So let's solve for t. T is just going to be, mg over cosine theta, and then I'm going to plug t right in there so I can figure out what a is. So it looks to me like this is going to be mg sine theta over cosine theta is equal to ma. Now the nice thing is it follows the usual pattern where the masses cancel. So you can use this thing as an accelerometer. It doesn't matter what's at the end of it. It doesn't matter if it's a heavy thing or a light thing. The mass cancels. So what this means is that the acceleration is just g tangent theta. Very cool. So if, suppose you watch this thing accelerate and the angle is 30 degrees, that implies that a is, let's see, tangent of 30 degrees, was that's like 0.58, I think, something like that. And then g is 10. We're always going to approximate g to be 10. So the acceleration is going to be like 5.8 meters per second squared. Cool. All right. So if you see that angle theta, then you know how fast this thing is accelerating. There's the little complication I sort of alluded to before, which is that's all cool if you're watching the car from like a sidewalk, if you're watching it accelerate and you see this angle. What if you're inside the car? Just for a second, let's talk about what happens if you're inside the car, because it's a little bit weird if you're inside the car. You'll see that same angle, right? Everyone's going to agree about that angle. So if you're sitting inside the car, you see that this thing is making an angle, but it doesn't seem like it's accelerating, right? Because you're accelerating along with it. And the problem is this is generally true. You run into trouble if you're in an accelerated frame and you take measurements like this. So if you're in the car, you would still set this up as your free body diagram. Gravity's acting down, the tension's acting along the chord, makes an angle theta. But look at that free body diagram. If you're in the car, the problem with this is that those forces don't balance, right? In order for this thing, here's what I'm saying. In order for these things to balance so that this thing doesn't accelerate, so it stays static, in order for these things to balance, it's possible that the y component of t could equal mg. That's certainly possible. But look, there's no x component. There's that x component of t left over and nothing to balance it, right? You would have to make up. Here's the point. You would have to make up. I'm going to put it in another color so we don't take it seriously. You would have to make up some other force acting, let's say, back that way, pulling the mass back that way in order to get everything to balance. In physics, these are called hopefully I spelled that right. Fictitious? I think I spelled it right. Fictitious forces. In other words, it doesn't really exist. It certainly feels like it does. If you're sitting in the passenger seat and someone accelerates the car forward, you sort of feel, and we talk like this all the time, you say, oh, something is pushing me back into the seat, right? The acceleration drove me back into the seat. And you would think something has to be pulling that mass back to make that angle. But really, it's a fictitious force. What force could possibly be doing that? Nothing is touching the mass. There's no big gravitational force that way. There's nothing that could be pulling the mass back. So in physics, these are called fictitious forces, and they arise inside of accelerated systems. The error is that we're making these measurements inside an accelerated system. Because notice that if we look at this from the point of view of a sidewalk and a car going by, we don't need a fictitious force. This is perfectly fine because we have this acceleration. We know the thing is accelerating forward in the plus x direction, right? So we don't need to invent these fictitious forces to explain it. Okay, here's a little bit more. Here's a little bit more. What if we do this? Maybe I can draw this. Okay, now suppose it's not just hanging from a rear view mirror. Suppose we're not in a car anymore. Suppose we're just, I don't know if I can show it with this. Suppose we're just swinging this thing around so that the mass is making a horizontal circle. All right, so it's going to look something like that. Maybe that'll work. So the mass is going around in a circle like this. And what we might want to know is, this is a related problem because the faster the thing goes, the greater that angle is going to be. All right. So if we make an angle theta, how fast is the mass going around in that circle? That's another question we can ask. Okay, so if the motion is circular, how fast is it going? All right. Okay, nothing changes. The free body diagram is exactly the same, right? So still, A is G tangent theta. That doesn't change. That's still true. But if it's going around in a circle, what you might know from class is the acceleration is centripetal. It's pointed towards the center. And it's got a value, it's got a magnitude of v squared over r, right? That's how you tie acceleration in circular motion to a speed, v. Neat. So we can do that. This means if a is v squared over r, then v, just with a tiny bit of algebra, then v is rg tangent theta. Cool. So that's the speed you need to travel at. It's terrible English. In order to go around a circle that makes an angle theta with the vertical. So again, if it's 30 degrees, let's say, now we need to tell you what that R is. R is the length of that string. Oh, no, I'm sorry. No, it's not. R is, R is the radius of that circle, the radius of that circle, right? The radius of the circular motion. So if, let's just see, if R is, let's say 50 centimeters. So if that's like a meter all the way across the circle, and theta is 30 degrees again, that means that my speed is going to be, let's see, I did it already, 1.7 meters per second. Neat. So knowing that angle, it tells you what the speed of the object has to be as it goes around in the circle. And then the one other thing that we'll do, because we'll use this as we go along, is converting from a speed around a circle to usually a measure that we use more often is RPM, right? Revolutions per minute. That's a really common way to express the rate at which something goes around in a circle. So how do we convert? If we know the R, how do we convert from speed to RPM? Sometimes it's difficult to know what letter to use for RPMs. I'm just going to introduce one, and I'll try to be consistent. I'm going to call that a capital omega. For kind of reasons you'll see later, as we go along, we're going to use something else describing circular motion as little omega. So capital omega, I don't know, I'll just use that. Hopefully I'll be consistent. Okay, so how do we convert? We'll do it formally, and then we'll do a shortcut. So if I have 1.7 meters per second, and I want to convert to revolutions per minute. Okay, the first thing I'm going to do is get rid of the seconds. 60 seconds per minute. So this is just dimensional analysis. Cool, so now I've got meters per minute. I need to do revolutions, right? So I need to put in revolutions per meter, and then I'm all set. So if I do revolutions, how many meters are in a revolution? Well, we know that it's a circle, right? So if I go all the way around the circle once, how many meters is that? It's just 2 pi times r meters. Okay, so that's going to cancel. So what I've got left over, revolutions per minute, RPM. Neat. So if I do this, what I'm going to get is about 32, what did I get? 32.4 RPM. Neat. Now here's the shortcut. So here's what we're going to do from now on. I mean, this is the formal way for finding out what that conversion factor is. But let's look at it, because maybe we can do this quick, because doing this over and over and over again is going to be really boring. So look, this bit, here's the conversion factor right there. Let's look at that bit real quick. I got the R in the bottom. That's the thing that's going to be different for every circle, is the R. But look, I've got a 60 and a 2 pi. What is pi? It's a little bit bigger than 3. I don't know. It's kind of 3. It's roughly 3. 2 times 3 is 6. So pretty much 60 over 2 pi approximately is just 10. Pretty much. It's just 10. So if we're just going to approximate stuff and get it quick, here's what we can do. That's just 10 divided by r. So the conversion factor in going from meters per second to RPM is you just multiply 1.7 times 10 over r. My r was 50 centimeters, half a meter. 10 over a half is like 20, right? 20 times 1.7 is going to be right around 34. So 32.4 is the exact answer. The approximate answer is going to be about 34. in videos, just because I'm not real interested in determining things real precisely in calculations, we will rarely do the exact thing down here, the 32.4 thing. More often, I'm just going to say going from meters per second to RPMs is going to be 10 over R. That's going to be easy and quick. So feel free to use it. If you're in a lab or you're trying to actually build something and you need to be precise, then use the precise thing. But if you're just trying to get a handle on roughly what the answer is, let's approximate stuff. Let's say that's 10 over R. Very cool. All right, so that is how to handle these masses in accelerated frames, and we got more coming up.